Okay, so for an example, let's suppose that we have a sample of 36 cuttlefish lengths. Cuttlefish are cephalopods, similar to octopi and squids. And we find a sample standard deviation of 1.36 centimeters. And let's suppose we're going to find a 98% confidence interval for sigma, which is the population standard deviation of cuttlefish lengths. Obviously, we couldn't go out and sample all cuttlefish in the world, so we'll have to use this sample to estimate. So we want to make sure that we're hitting our target here for being able to use our technique that we discussed in the previous video. So first of all, examine the sample size, make sure that it's large enough. 36 is greater than 30, so that checks out. And the variable that we're measuring, the underlying distribution should be normal. Lengths and measurements of anatomy are usually normally distributed, so we're good to go there. Obviously, this is where you need the expertise sometimes of your discipline or of somebody from that discipline to be able to really make those decisions, those calls on whether something would be reasonable to infer that a variable that you're measuring is normally distributed. And we're given that our alpha then, in this case, because our confidence level is 98%, which means alpha is 0.02. And in order to find the critical values, then we'll cut that in half and use a table or a calculator, right? So first things first, what's our target? We're going to estimate sigma. So we're going to take the square root of the endpoints from the confidence interval for variance. We need the degrees of freedom. So degrees of freedom, remember that's n minus 1, so that's 35. And we want to find the critical values for the chi-square distribution on the right tail and on the left tail. So for the right tail, right, we want an area of 0.01. So if we find that then we find that this is 57.34 roughly. And then on the other hand, the left and critical value is going to be 18.51. And I'm using an online calculator here. It's an applet which calculates all sorts of things related to a chi-square distribution, but you should be able to use a table like the one in the appendix. Or if your TI calculator has additional percentile calculators, you can use that as well. Now that we have that, we can construct our confidence interval. So n minus 1 times s squared, which is our sample variance, divided by the right tail critical value, all square rooted, and the only difference for the right tail is that we're now dividing by the left critical value. Okay, so if you're paying attention, this means 35 times 1.36 squared divided by 57.34, all square rooted, if you have a calculator handy, now would be a good time to use that. Try to stick to 2 places after the decimal or 3 if necessary. That might be more than enough. And I'm calculating it now. If you have a handheld calculator, just make sure that you're appropriately using parentheses where you need them. So here I'm getting the square root of 1.129 less than sigma, less than the square root of 35 times 1.36 squared and on the right side we have the square root of 3.497. But luckily, then all we need to do then is to take the square root of these values and we'll find our endpoints. Actually, that's closer to 3. And the square root of 3.497. Which is 1.870. So this is our confidence interval now for standard deviation. So we're saying that at the 98% confidence level, we estimate that the population standard deviation is between 1.063 and 1.870 centimeters. And we get almost for free the variance confidence interval, because all we would have had to do is not taken the square root. So this is for the variance. And just make sure that you have the appropriate units on this once you get this done.